Hey, hi. Good morning, everyone. Let's start. Let me share a few files with you. Just one minute. I'm sharing one code and one data set with you. Open the code in the collab. Open the code in the collab or Jupyter Notebook, whatever you're comfortable with. Let me know when you have it open.
Open.
Everyone have it open? Can we start? Okay. Then the first part of the code is uh, uploading the file to the server, right? Let's say in this case. So what we are doing is we are importing the file from our local, that is our laptop, to the server from which Colab will be able to later read the file.
Can you please increase the font size? It's too small.
Okay, sure. Let me know. This is fine.
A bit more. Yeah, it's fine. Thank you.
Okay. In the first part of the code, what we are doing is we are trying to read the file, upload the file. It says I will go to the location where I've kept the file. It's done. Now in the second part of the code, we are reading that file into a variable now. Okay, so we are creating a data set, cars. If you're using Jupyter Notebook, then you might have to use the second code, not the first one. Okay, if you're using Colab, then first code. If you're using Jupyter Notebook, then second code. Okay. Then I'm reading a few libraries, right? Let's say, for example, a few of it you're already aware of: NumPys, Matplotlib, Seaborn, right? And sklearn is a very popular library for machine learning. For a lot of other machine learning models as well, we will be importing sklearn. So I'll read this. Then the first thing that we are doing is we are trying to see what is the schema of our table. Okay. How many columns are there? What is the column types and so on. So it looks like I have in total three columns. One is car ID, one is horsepower, and another one is price. Okay. So three in total columns we have. In each column, I have 205 known null values. So it means that there are 205 rows. Okay. And there is no missing value in car ID or horsepower or price column. Okay. Car ID column is integer. Horsepower column is integer. Price is our decimals. Right. So the data types make sense. There is no missing value. In total, there are three variables that we have. Now in this, our target variable is going to be, if I look at the top 5 rows, right, of this data set, my target variable is going to be price. And my input variable is going to be your
Horsepower.
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 horsepower, not car ID. Should I use
No,
car
No,
ID?
not required.
Why? Why not required?
I think it's car ID because it's unique.
It is unique for every car, so car ID is
Horsepower
important.
values can be like duplicate, like 11, yeah, like 111. The car
there
ID
is
will be unique, so we should choose that.
Mm-hmm.
there is no correlation between the car ID and price.
Not exactly. So what is car ID here, right? Car ID here is
Unique.
nothing. Mm-hmm.
There is a unique value for means,
Right. So it is a unique value that you have just assigned to each car, right? Is there any logic behind assigning that car ID? The answer is no. Okay. For example, if I'm trying to predict, you know, what should I say? Yeah, let's say I'm trying to predict whether you are a um, person who will return the loan or not. Let's say for a bank, if I'm trying to predict whether this person is going to return the loan or not, right? Will your bank account number will be a good variable,
Yes.
or your phone number will it that be a very good variable?
no.
Anything that is unique to us will be a great variable.
Yeah, it is not just about the uniqueness, but also, you know, like how that variable was created. If it is just a number which is randomly assigned, then obviously it will not have any impact on our target. Similarly, your phone number will not have any impact on your credit score. Your bank account number will not have any impact on your credit score. Your Aadhaar number will not have any impact on your credit score, because all of these numbers are randomly generated and assigned to someone. Okay. Similarly, here the car ID is not assigned using some logic. Okay. Car ID is just a random number to identify each car. So these kind of variables are in general useless to make any prediction. Okay.
Can you
One
show the question like on what you are showing the code?
Sorry, what do you want, Likita?
The question like I joined bit late. Like
Uh-huh.
like What program are you explaining about the question I'm asking?
Okay. So I've already shared the code and the data set. What we have is we are trying to solve for simple linear regression in which we will be having only one variable and one target variable. Okay. So it's just a car's data set and we're just discussing that there are three columns in it: car ID, horsepower, and price. And we will be using horsepower as a variable and we will try to predict price of the car. Okay. Now,
Puneet,
uh-huh.
so consider we have a multiple columns, and how we can means is there are methods that we can select which columns we need to uh, choose so that means uh, to
Mhm.
increase the accuracy.
Right. Okay. So we do have that. When we will discuss the multilinear regression, we will discuss that part.
Okay.
Okay. So assuming now for now that we have only one variable, that is horsepower, and the second variable is price. This is price is our target variable. So which one is a dependent variable and which one is an independent variable?
Uh, Price is the dependent and horsepower is the independent.
Very nice, right? So so our target variable is called dependent variable. Okay, because it will depend on other variables, right? At the same time, our input variables are also called independent variables. Okay, this is a terminology that you should remember. Your target variable is called dependent variable and your input variables are called independent variables. Okay. Now, in general, what I expect is that as your horsepower will increase, the price of the car will also increase. Make sense? Right?
Yes.
If I increase the horsepower, sorry, I think I said the opposite. When the horsepower of the car will increase, okay, most probably the price of the car will also increase. Bigger the engine, more powerful the engine is, more is going to be the price of the car.
Sir,
Okay.
one question here.
Mhm.
Sir, car ID is 1 and 2 are having same horsepower, but it is showing different price.
Right.
Then while deciding the price, how will we, evaluate like
Right.
what's the
So,
correct thing?
right. So for deciding the price of the car, horsepower will not be the only variable, right? Maybe the dimension of the car is also important. Whether it is a front wheel drive, rear wheel drive, right? And similarly, what are the other features that we have in that? Let's say, for example, whether we have a ventilated seats or not, whether we have a 360-degree camera or not. So many other things are there which can change the price of the car. But here we are just assuming that we have only one variable.
Yeah. Okay.
Okay. Yeah. So the more the relevant variable you will add, more accurate the model will become. So yeah. Now in the next part, what we are doing is, so car ID is an integer, horsepower is an integer, price is in decimals. Makes sense. It's just that it's always a good habit to convert the car ID kind of variables to string. Okay, I know that we will not be using it in the machine learning model, but still it's a good habit that always change the ID variables to string because these are not integer variables. Okay, your phone number, your Aadhaar card number, your bank account number, any ID, employee ID and all, these are not integer variables. These are string variables or categorical variables. Okay, so it's always a good habit to change them back to categorical, and that's what I have done over here. Okay, although even if you keep it like this, it is totally fine because I'm not going to use it, but it is a good habit to keep the data types correct for each column. Okay, now we are just checking the sample rows again to see whether whether the data set is still looking fine or not after making the type conversion. Okay. The next part that I want to do is, because we are solving for linear regression, right? And correlation can be a very important metrics here. Why correlation will be an important metric? What correlation gives us?
It gives how they are related, positive or negative, how they are changes if the values increase on the other side. The basis of that, it will try to predict the outcome in the future by combining all of that.
Right, right. So actually, correlation gives me whether two variables are linearly related or not, right? And that's what exactly we are doing in linear regression. We are seeing whether two variables, sorry, my bad, right? The same thing we are doing in linear regression as well. We are checking whether, the variables are linearly related or not. Okay. So correlation is going to be a very important metric here, because what correlation do and what linear regression do is kind of more or less the same thing. Okay. So for the first thing that I'm doing is I'm writing a generic code so that we can use it later also. I'm first selecting all the variables which are of either integer or float type. That is, I'm only choosing the numeric columns. Why I'm doing that? Because correlation can only be defined for numeric columns. It cannot be defined for categorical columns. So before creating the correlation metric, right, what I'm doing is I'm only selecting those variables which are integers. So here, when I'm looking for integer variables, I have two, that is horsepower and price. And in the next line of code, I'm just using this core function, CORR, and that will give me what is the correlation between different variables. Okay. For example, the correlation value between horsepower and horsepower will be 1. A variable is always perfectly correlated with itself. Similarly, the correlation between price and price is 1. Makes sense, right? A variable is perfectly correlated with itself. Correlation between horsepower and price is 0.81. And similarly, between price and horsepower is also 0.81, right? Whether you are calculating correlation between variable 1 and variable 2, or variable 2 and variable 1, it does not matter. It will give you the same value. Okay. That's why the correlation value between horsepower versus price and price versus horsepower is exactly the same. That is 0.81.
Sir, this correlation, is it the same thing what we discussed, like correlation, covariance?
Right. Yes.
Same thing only, right?
Right. Right. Yes. Okay. So now we have a correlation value of 0.8. Is it the high correlation, low correlation?
It's high.
High,
It's a high
High
correlation value.
high
correlation.
positive.
In general, everything above 0.7 or 0.75 is considered high. So here the correlation is high between horsepower and price. Okay, so it means that as the horsepower will increase, the price will also increase. Okay, now before we move to the next part, first of all, you guys also run the code till this point. Second thing is also create what it is called, scatter plot between horsepower and price. Okay, this is a task for you for now. Create a scatter plot between horsepower and price. Okay, so do both the things. First, run codes. Yeah, like using AI these days, we have everything. So it's gonna create the code between the plot between horsepower and price. So you can see that as the horsepower is increasing, the price is also increasing. Okay, can you please run the codes till this point and let me know if you have any question at any code. If you feel that you are not being able to understand what is happening there, ask me. I'll wait for 2 minutes.
Oh, the table horsepower and price and horsepower and price. I didn't get that table.
Just 1 minute. See, it is a metric. This one, right? Right, Sindhana, this one you're referring to?
Yes, yes.
Right. This is like I could have calculated just only one value also, horsepower price, and it will give you 0.81. Okay. It's just that I have created it in this format because when you have multiple variables, this format is in general like easy to understand. For example, if I have between one variable one and variable two, I want to find the correlation value. I will take 0.81. Done. Which is nice when you have two variables. But what if you have multiple variables? Then you will start writing v1 and v3, v1 and v4, then v2 and v3, v2 and v4, v3 and like so on, right? When you have multiple variables, it will make a long list. So instead of that, what we do is we create a metric. Let's say v1 here, v2 here, v3 here, right? Similarly, I will have here, and then I will just have the correlation values here. Let's say, like for example, this will always be 1, right? And let's say this is 81 0.33, right? And similarly, so some values will be there. Right? So now using this metric, whenever if I want to calculate what is the correlation between variable 1 and variable 2, this will be a correlation value.
Okay.
Okay, so it becomes like easy to follow, like this kind of a metric you will have. Okay, let me just create this one. 0.7, 0.87, 0.11, right? And similarly, so along the diagonal, this table will be the mirror image. Let's say, for example, between variable 1 and variable 2, it will be same as variable 2 versus variable 1, right? Between variable 3 and variable 1, it will be same as what is between variable 3 and variable 1. So this kind of a metric will get created. This is called correlation matrix. Okay, so from this metric, if you want to calculate the correlation value between any two variable, you can easily check like, okay, between variable 1 and variable 2, this is the correlation. Yeah. So for that, I have written a generic code here. So tomorrow, if you will have more number of variables also, right, it will create a plot like 5 by 5 or 10 by 10, and it will be easy to calculate the correlation between any two. Okay, in the next part, what we are doing is we are splitting the data into X and Y. Again, a very standard process you will see that I will separate the input variables with the target variable. So my input variable is horsepower and my target variable is price. So I'm separating these two.
Punit, the code is not directly opening in this website.
No, it will. You just need to go to file and upload notebook.
Mm,
It will open for sure. Let me know if it's still not working. You can share your screen and I will help you out.
yeah, I will try.
Mm.
Puneet, this is working for notebook also. It has collab commands there.
For Jupyter Notebook, yes, it will work. It's just that a few commands you would have to change. For example, this is not required.
Yeah.
Yeah, this much, right? So you can remove this, and then instead of running the first command, you can run the second command.
Okay.
That's it. After this, it will exactly be the same.
Okay. Sure.
So I have separated the input variable and the target variable. Input variable is horsepower. If there were like 5 different variables, I will put all the 5 variables here, right? And you will keep the target variable separate. Okay. Now what I will do is the second part is I will be splitting the data into test and train, right? As we had discussed, what we need to do is we keep 80% of the data for training and 20% of data for testing. Training data, like scene data on which the model will be able to see both questions and answer, right? What is the input variable also and what is the target. Both values will be exposed to the model. But from the test data, I will only expose the input variable and not the target variable. Okay. So my model will have an opportunity to learn the pattern from the training data, and then the same learning we will try to apply on the test data. Okay. So first part is nothing but I'm importing that model. In the second part, what I'm doing is I'm adding one constant. Okay. Why I'm adding a constant? Let me explain. Okay. Right now, our equation for simple linear regression is y equal to, okay, equation for simple linear regression is y equal to what?
mx plus
Beta
c,
naught
mx
plus beta
c.
1.
beta naught plus
Beta 1 x1
beta 1 plus beta
beta.
0.
Okay. Now, the model that we are, so the Python is an open source language. Okay. It means that anyone can create their packages and publish it. Okay. Now, for the package that we are using, there are multiple packages for doing linear regression. The one that we are using it has one limitation. The limitation is it cannot create beta naught. Okay, all it can do is it can create just predict beta 1. So let's say even if I have multiple linear regression, which is y is equal to beta 1 x1 plus beta 2 x2 plus beta 3 x3 plus beta naught, let's say. Even in this case, my model, the one that I'm using, will be able to predict beta 1, beta 2, beta 3, but beta naught, it won't be able to predict. Okay, the package that we are using, it has that limitation. So what we do is, if I want to do simple linear regression, I add one more variable. So you already have one variable, let's say horsepower, right? Your horsepower will be, let's say 110, 120, 132, 116, 119, and so on, right? I'm creating one more variable that is x2. That variable is 1 everywhere. It is just 1 everywhere. And then I'm using both of these variables for prediction. Now what is going to happen is I will get a equation which is y is equal to, let's say, something beta, some beta 1 into horsepower plus some beta 2 into x2, this variable, a constant, right? Plus beta 0 will not be able to calculate. Beta 0 I won't be able to calculate because my package doesn't give beta 0. Okay, so what I will get is y is equal to beta 1 into horsepower plus beta 2 into x2. But what is the value of x2?
1.
1.
1, right?
1.
Can I simply write this as y is equal to beta 1 into horsepower plus beta 2, right? Which will be similar to y is equal to beta 1 horsepower plus beta 0. You got my point, what we are doing?
Sir, can you please repeat it?
Right. I was saying that this is the equation that I want to predict. Y is equal to beta 1 x1 plus beta 0. That's correct. Now, the package that we are using is that package says that I cannot predict beta 0. You need to have a variable, only then I will be able to predict the coefficient. So I said that, okay, I will give you a variable. I gave that variable, equation, a variable x2, which is 1 everywhere. So because my model cannot predict beta 0, my model predicted this. Right? Something like y is equal to 39 horsepower plus, let's say, x2. Sorry, my bad. Not just x2, beta 2 x2. But what is the value of x2 everywhere?
1.
1, right? So I can simply write this equation. Y is equal to 39, let's say, horsepower plus beta 2, right? Assuming beta 2 to be 10, y is equal to 39 horsepower plus 10, right? So this equation that you see over here, is it not in the format of y is equal to beta 1 x1 plus beta naught? This equation,
Yes, yes.
right? Right. Same
Every
thing here.
model cannot predict this.
No, so it depends upon which package you are using.
Okay.
I'm using this particular package because the way it shows result, it's easy to understand as compared to what other, like how other other functions show the model. Okay, so every model or every function has their own advantage and disadvantage. I really like this one because the output is very much sorted as compared to the other functions that we have. Only one limitation is there, that it cannot predict beta naught, and that we can easily overcome by creating a constant. Okay, so here in this case we added a constant, this, which is 1 everywhere. So the coefficient of this constant will give me beta naught. Clear? Any question, anyone?
So what are the other packages that it can handle?
Sorry, what are the other?
What are the other packages that can handle this, this beta 0 problem without re-adding?
Yeah, I can share. I don't remember the names, but there are actually many, to be very frank. But I will Google and I will share the names with you.
Okay, okay. And
Okay.
one more thing, sir, that fitting a linear model, statsmodel.api, what is that library used for exactly?
This one.
Yes, statsmodel.api.
Right, right. So I didn't get it. What do you mean by that? This is just a library, right?
I mean, why are we using that? Just to create that beta zero.
No, no, no. We let's say if you look at it, we are using two things from there. From this SM, two things are used. One is to add a constant, right? Here.
Yeah.
And the second time is when I'm performing the linear regression itself. So this OLS function, it is called ordinary least square. This is again regression type,
Okay.
right? So the both the function, this one also and this add constant, both the functions are coming from the same
Okay.
theory,
Okay. So got it. Yeah.
right?
Here, X has the value as horsepower, right?
X is this one you're asking?
Yeah.
Right. So X is a data set in which we have the input variables. Earlier it had only one variable, horsepower. Now it has two variables. One is horsepower, other one is constant.
So it
Okay.
will become horsepower plus one, like this.
No, not plus one. Two separate columns. Right? This is a constant column. This is a horsepower column.
So this X value, it will vary each time we run it, or it will always be one only?
It will always be one. If it will
Uh,
vary every time, then I will have a problem, right?
mm,
I cannot replace this x2 by 1 then.
Okay.
Okay.
So that X is equal to SM dot constant, that line that will give X value as one.
Right. Always.
Okay.
Okay. In the next, any other question, anyone?
I have a question like apart from one, it was like something else. In the case of that, like in our case, it's all one, X2 is all one.
Uh-huh.
But if we have like something other than one,
Mm-hmm.
like zero, because like according to me, it's like saying it's true. I'm like perceiving it as a true value because one is true.
Right.
So there's some variable where like this horsepower have like it's true. Something is true. This horsepower is
Mm-hmm.
true. But
Mm-hmm.
apart from one, if we have like zero,
Okay.
so like I haven't done it like in this way, like in important libraries. I like code it from scratch. I make like sigmoid function. Then I like make like linear regression from that, write it that we have learned in like stats, the
Mm-hmm.
all the formulas.
Mm-hmm.
So like here we'll just add the constant from x. But like in Scratch version, we can just like assign the variable
Yeah,
and
you
return
can
it.
you can have it. Right. You can simply say x constant like a new column is equal to 1 also. Same thing.
Yeah, that can be good.
Yeah, right.
So Puneet, why we are making it as add constant? So
Why we are adding one constant here? This is what you asked me.
yeah.
The thing that I explained here, right? I
Yep.
cannot get beta naught. So I'm getting a way around to kind of get the value of beta naught. Okay. My function does not give me beta naught. And that's why what I'm doing is I'm creating a one more variable x2, which is one everywhere. Okay. So my equation will look something like this. Y is equal to 39 horsepower plus let's say beta 2 x2. But because x2 is 1 everywhere, I will get y is equal to 39 horsepower plus beta 2, which is a constant, right? So it will be same as beta naught. This B2 will become beta naught.
So if we have another variable also, like other than horsepower, something like engine power, something.
Right.
So this equation will work, right?
Right. It will work. So then it will become like 39 horsepower, let's say plus 42 weight of the car, right? Plus let's say 12 times height of the car, plus let's say beta 2, right? This one, which
Okay.
will be a constant. Yeah.
Okay. Can you please show the code once?
Yeah, sure.
Yeah, so here that train test split is there, right? From Skylar model selection import.
Right.
So is
This one.
that user define our our notation, or is that
No, this is a
Otherwise, we
standard
have
one.
to, that is
This
a
is a,
standard one. We have to follow, these two lines are fixed, right? Whenever we want to run
Mhm.
this thing, so these two lines are fixed, right? Then X,
Right,
X test,
exactly.
Y train, Y test, everything.
Right, exactly. Yes. Okay. When I will be running this other code of linear regression, okay, for multilinear regression, you will see that I'm using exactly the same code. Nothing will change in this. Okay. From top to bottom, nothing will change. I will just run as it is.
Okay. So here, where is our car data set here actually?
It is X. So I had defined, let's say here,
Okay.
X as horsepower, Y as price of the car. So here I am importing my input variable and my target variable.
Okay. So we just have to give that variable names only here. That
Right, exactly. And rest of the things will be exactly the same.
okay. If we have one more variable, then
Then it will be,
one
let's say, here.
X2, something like that.
Right. Let's say, for example, horsepower, and let's say weight of the car. That's it.
Okay.
Everything will remain same. I'll just run this, and I need not to change anything here. As it is, I will run.
Okay. Okay. Yeah. Thank you.
Okay.
Puneet, what we are exactly finding by running this code?
We are as of now we are just splitting the data set into two parts, that is train and test. Train size we are keeping it at 80%. The 0.8 means I'm keeping it as 80%. Test means 0.2 means that I'm keeping the test data as remaining 20%. Okay. On the 80% of the data, I will be training my model. On 20% data, I will be testing my model.
Like you are testing your model to find the prices, right?
Right, yes.
By
Yes.
taking the this as
I,
input
yeah,
horsepower.
exactly. Okay, so in this line of code, what we are doing is we are splitting the data set into test and train. Again, a very standard line in all the machine learning codes that we will run. This line will remain as it is. Okay, whether it will be linear regression, logistic regression, random forest, everywhere this line will be there, and it will be exactly the same as this. And what we are getting is we are getting 4 outputs from this line of code. One, I'm getting X-train, that is questions for training. Okay, this is questions for testing. This is the answer key of training data set. This is answer key of test data set. So when I'm training the model, I will be giving questions as well. This is my questions. I will be giving answers as well. That is, I'm providing what is the horsepower and what is the price associated with that horsepower. So while training, I will give both. Like when you are teaching a student addition, you will just not tell 2 plus 2. You tell him 2 plus 2 is 4. 3 plus 9 is 12. So you need to give him question as well, the answer as well for training. And that's why I'm giving both the horsepower and the price. Okay, for the next one, let me run this code. So the model is ready. When we ran this code, the model is already ready. Okay. Now in the next part, what we are doing is we are trying to create the summary of our model. Okay, let me run this. This is summary of our model. Okay, here these are the coefficients. So this is constant. This constant's coefficient is -3283. For horsepower, the coefficient is 158. Okay, what is the meaning of that? It means that now if I have to create if I have to write the linear regression equation, it will be y is equal to 1.5, let's say 1.59, 159, or okay, 158.78 horsepower plus your minus here 3283 multiplied by constant. What is the value of constant?
1.
1, right? So I will simply write it as done. Okay. Now this is a which format? This is this format. Y is equal to beta 1 x1
plus beta.
beta 1. Okay, where beta 1 is what? 158.78. Beta 0 is what? Minus 3283. Okay, now for any given horsepower, if my horsepower is 100, just for simplicity's sake, if someone will ask me, if I'm launching a new car where the horsepower is 100, what is going to be the price of the car? What is the predicted price of a car if the horsepower is 100? So it is going to be price is equal to 158.78 multiplied by 100 minus 3283.
Then how we develop these coefficients? 158.78.
Yeah, sure. Just 1 minute. 15878 minus 3283, right? 3283. 125. It is 12595, right? So this is going to be my prediction. If horsepower is 100 and if I want to predict the price, right? How these values are coming? This 158.78 is coming from here. Coefficient, right? Similarly, the constant coefficient is minus 3283. Right? So these two are the most important metrics for us.
Like how it's showing this data in the summary?
How we are showing it? Like using this code.
How it generated, I'm asking. Through input values?
Yeah, so we had this model that we had trained, right? We just give that model here, model.summary, and that will give me the summary of the model. Okay, now here in this, there are a lot of different things which are there. Okay, but the main thing that you need to know is one is R square, this one. Okay, we will discuss this later, what R square means. Second thing is the coefficients. Third thing is the p-value. Okay, why the p-value is important? Because p-value tells me whether the
whether
so
to reject or accept the model.
exactly, not the model but the variable,
Variable.
right? So in the linear regression here we are having a p-value. Okay, what is this p-value? First of all, for every p-value, always remember, whenever you have a p-value, it is coming from some test, some hypothesis testing. Okay, so for this value, we have to, it's just additional information. No one is going to ask you this, but again, for this p-value that you see over here, this is the p-value. Okay, for this p-value that you see over here, the null hypothesis is coefficient of the variable is 0. And our alternate hypothesis is opposite of this. Coefficient of the variable is non-zero.
Sir, is it coefficient of the variable is 0 or 1?
0.
Okay.
Coefficient is what? Coefficient is this, right? This is coefficient. I will explain. Now, tell me if the p-value is less than alpha, right? That is 5%. Do we reject the null hypothesis or accept the null hypothesis?
Reject the null hypothesis.
Right?
Yeah.
Here, the p-value is less than 0.05.
Yes.
Right? So we will be rejecting the null hypothesis because our p-value is, right? Our p-value is less than 0.05 for both the variables. You will check first for the first variable and for second variable also. Like everywhere the p-value is less than 0.05. So what we will be doing is we will reject this one. As p-value is less than alpha, we will reject this and we will accept this. So we are saying that the coefficients are non-zero. Okay, these coefficients that we are having, we are confident that they are not 0. Okay, what if it was 0? What if my hypothesis testing say that it can be 0? If it can be 0, then that variable is not important. Why it is not important? Just imagine. Y is equal to beta 1 x1 plus beta 2 x2 plus beta naught. If someone will say beta 2 is approximately equal to 0. If someone is going to say that beta 2 is going to be equal to 0, right? Does it matter what is the value of x2 is?
No.
No, right? x2 can have any value it wants, right? It is not going to change my target variable. Okay, so it means that x2 is a useless variable. I need not to add it into my modeling because whatever is going to be the value of x2, it will be close to like this whole thing will become close to 0 if b2 is 0. Doesn't matter what is the value of x2 is. So I need not to have x2 in my model. That's what the benefit of p-value is. If p-value is greater than 0.05, I'm going to accept the null hypothesis, that is the coefficient is close to 0. But when the p-value is less than 0.05, I can say that the coefficient is not close to 0. That's why the variable is important. Okay, any question on this? Stevie, there is no difference at all, right? These are just different tools. You can use Python, you can use R, you can use a software, you can use Excel also. In Excel also, you can do linear regression. for a small data set, it will give you exactly the same result. Okay, these are just different means of running linear regression. Okay, let's say, for example, yesterday we were manually doing it here, right? Whatever the linear regression equation was, we were able to kind of come up with on our own, right? Let's say 12. So whatever this equation was, we were able to predict it on our own. So we were doing it in Excel. There is other ways of doing it in Excel also. Similarly, today we are doing it in Python. Someone can also do it in stat software. Okay, any doubt, anyone?
No.
Cool. Okay.
Sir, we are discussing, like, we are creating a model. Then again, why that testing part come into picture? Like H0 and H1, is it greater than 0 or non-zero?
Right, right. So when we are creating a model, right, then the model is just telling you that this is the best possible equation that I could have come up with. Okay, I could have come up with. But null hypothesis testing, this hypothesis testing tells me that if you will do this modeling again and again, let's say with a little bit different data set, what are the chances that this coefficient might come as 0? If you will repeat this exercise again and again, okay, what are the chances that it might come 0? It's like, see, here it is 158, which is way above the, what I would say, 0 value. Okay, so that's why the p-value is very close to 0. But if this was like approximately maybe 2, 3, right, then in those cases, there can be a chance that that value is exact kind of close to 0 only. So null hypothesis tells me that what are the chances if you will do this modeling exercise again and again, repeat this with a little bit different data set, that this value might come as 0. Okay, model is just telling me that for this data set, this value is 158, right? Hypothesis testing is telling me in this case that if I will repeat this experiment again and again, okay, then what are the chances that I will get a 0 coefficient?
If 0 coefficient means there is nothing, right? Like y is equal to mx plus c. If that m is 0,
right?
Coefficient is that m only, right?
Right, right.
Yeah.
Yes.
So that means y is equal to 0. That
No,
becomes 0,
no,
right? Constant.
no. Right, right. So actually there is not just one variable. Y is equal to beta 1 x1 plus beta 2 x2 plus beta 3 x3. So when the p-value is less than greater than alpha, right, then we are saying that most probably for this particular variable, the coefficient is 0. Okay, so I don't need x1 in that case, but I can, so this will become 0.
Right.
Plus, but beta 2 is also there, right? Beta 3 is also there. Okay, so it will not become 0. But that variable is not needed.
Okay. So
Okay.
if can you please show that other slide?
Yeah. Slide, okay.
Not the slide, that code.
Okay.
Yeah, so here if horsepower p-value is coming as 0.000,
Right.
so what are we interpreting this? Are we
Right.
rejecting this horsepower?
No, no. Here the p-value is less than 5%. Is that correct?
Right, right.
If it is less than 5%, we will be rejecting the null hypothesis.
Right.
Right? What is our null hypothesis? That the coefficient is 0. So we are rejecting this, that this is not correct.
Okay.
Right? So we will be keeping horsepower.
So we are accepting the horsepower of 158. We are
Yes.
accepting that it is non-zero and this 158.
Right. Yes. Nice.
Okay. So if we get some values, like if we have 3 or 4 variables here, like horsepower, weight something. So if we get weight as greater than 0.5 and horsepower as 0.00, then in that case, what do we conclude?
We will remove weight and we will rerun the model.
Okay.
Okay, because then my hypothesis testing is telling me that if I will repeat this experiment again and again, right, the coefficient might come 0 for weight. Okay, that is weight is not an important variable.
Okay, whatever variables has less than
0.05.
0.5 only, then we are accepting that.
Right, exactly.
Okay.
It's showing something like outliers.
It's not outliers, it's more of a like how much related this particular variable is to your target. As I was telling you, right? Let's say if I will like price of the car, right? Here, weight, height of the car, whether it is a horsepower, it's four-wheel drive, front-wheel drive. All of these are important variables, right? But
Yeah, I
when
got that. I'm coming to this negative hypothesis and all. So what I'm telling is, if we are rejecting, if suppose there are 4 to 5 variables and one we are rejecting, okay, so the feature itself we are deleting. Okay, it's not related to data. Got it.
Yes.
Yeah, thank you.
Sure.
And what does this standard error says here?
Like standard error is nothing but whenever if you look at this is the t value, right? So in t value, it is in general the formula is xi minus mu divided by sigma, right?
Right.
Right. This sigma is considered a standard error. So everywhere this denominator will change. For example, in case of two sample t-test, it will be something like xi minus mu divided by sigma divided by under root n, right? If you remember.
Right.
Right. So in that case, that will become the standard error.
Okay.
Okay, so whatever is the denominator is in calculating the t value, that is considered standard error.
In the code, we are rejecting this first coefficient minus 3283.
Why you're saying that?
Like it's
No, let's see, for example, here I have not rejected this, I'm keeping it. Like, why do you think we are like removing this or rejecting this?
I just thought it is in minus, right? So
No,
yeah.
that doesn't matter. Even if it is negative, it is fine, no problem. Being negative is nothing related to whether it is important or not important. Okay. Sometimes there are few variables which are negatively related with the target, which is fine. Okay. Now, what we'll do in the next part is I will calculate the RMSE value. Okay. RMSE is nothing but root mean square error. So we want to see for what I'm doing is I'm predicting for training data set. What is this prediction means? I have already trained the model and now I'm asking my model the same questions on which I have trained the model. Whatever is covered in the class, the same questions are being asked and we are seeing how the model is performing on that data set. So it is telling me that, okay, you are getting on an average error of 4400. Then what I'm doing is I'm in the next part, I'm checking the accuracy of my model on the test data set. The questions that my model has not seen before. Okay, in this part, if you look at it, I have give an input of two things: y test and y predicted test. What was y test?
The real value
answers
of
for
y.
the test.
Right, yeah, exactly. It was the answers or the real values that we had. right? More like an answer key for this. And this is my predicted answers. This is what my model is saying the answer is. This is what the real values are. So I'm comparing just these two to get the RMSE value. Okay. In general, the RMSE value, the error will be higher on the test data set as compared to the training data set. Okay. So we can see the same.
It's
Okay,
error
next one.
value.
Yeah, this
It's
is error value.
something, right?
Yeah, this is error. Root means square error.
This value can be anything, any range, right? So
Yeah, right. It can be negative also, it can be positive, it can be anything. And that's why actually, Deepak, that's a very good question, because that's the reason that there is a need for R square value. Okay. As you said, here the range of error can be anything. Okay. When it comes to predicting categorical data set, or when it comes to predicting categorical target value, actually, okay, then the accuracy is measured in terms of percentage, right? Like 90%, 95%, 96%. But when there is a continuous variable, I cannot measure accuracy as like in percentage. Everyone get that why we cannot do that? Let's say we have two target variables, two different problem statements, like one Deepak is working on, one I'm working on. Okay. So I'm working on a model which will try to predict the height of someone. Okay. Deepak is trying to, work on a model set which will tell me whether I should give loan to a person or not. Okay. More like credit worthiness. Right? So these are the actual values that I'm going to write over here. Let's say 168, 139, 145, 155, 182. Like these are the actual values. 193, something like this. Right? And my predicted values are let's say 165, 140, 143, 157, 170, and let's say 195. Okay. On the other hand, for the model that Deepak was creating, it is about credit worthiness, whether I should be giving this person the loan or not. Okay. Now it can be that, okay, yes, I should give this person a loan. Let's say there are different customers. Right? This customer, I should not give the loan. These are the actual values. And let's say this is I should give. And then Deepak predicted, he was trying to predict. And then Deepak's prediction is that, okay, yes, I should give him the loan. Yes, I should give him the loan. No, I should not give him the loan. No, I should not give him. Yes. And let's say yes. So how Deepak's model accuracy will be measured? Deepak's model accuracy will be measured in this way that, okay, whether this is matching with this or not. Okay, in this case, it is matching. So this is right. In this case, it is not matching. In this case, it is matching. In this case, it is not matching. In this case, it is matching and matching. So it will be measured in terms of accuracy. Right? How many predictions that Deepak made? Deepak made 6 predictions. Out of these 6, how many were correct?
4.
4.
Right? So 2 by 3. So 66.6% accurate model Deepak has created. Now, when I will look at this, here I cannot measure accuracy in terms of whether it is matching or not. Because if I'll do it in that way, this is also wrong. This is also wrong. This is also wrong. This is also wrong. all are wrong, my accuracy is what? 0%. Right? So in case of continuous variable, we just don't directly match the two numbers and say whether it is matching or not. Because in continuous variable, we try to see how much close you were to the actual value. Okay, so this will not be the right way. What is the right way will be to see how much different your value was from the predicted value. So for example, I will say that here I had an error of close to 3. Here I had an error of close to 1. Here I had a error of 2. Here I had an error of 2. Here I had a error of 12. Here I had an error of 2. And maybe you will calculate a RMSE value, which come out might be 3. Right? So I'm telling you, on an average, there is an error of 3 in each prediction. Right? So accuracy will not make much sense here. What we should be calculating is RMSE. Here we can easily calculate accuracy. Right? So this is what the difference is when you try to predict a continuous variable, which is called regression, and versus when you try to predict a categorical variable, which is nothing but classification. Okay, so what Puneet is doing over here is nothing but, this is called regression. And what Deepak is doing over here is called classification. Okay, so for classification, the accuracy can be easily measured. For regression, we are stuck with things like RMSE. But there is a problem with RMSE, as Deepak was saying, that the range can be like here, the range is going to be the accuracy range can be what? What is the minimum and maximum accuracy?
+3 to -3, -3 to +3. Between that range, the predicted value should be there.
No, the accuracy range can be what for classification?
0 to 100.
0 to 1, right? It can be like all the values are incorrect, that is 0%, or all the values are correct, that can be 100%. Can the accuracy be more than 100%? No,
No.
right? Similarly, the accuracy cannot be less than 0% also. Okay, so for accuracy, I have a range 0 to 100%, and which makes evaluating the models very easy, right? That I know where I am right now, right? Because this is the maximum I can achieve, this is the worst I can do. But the problem with RMSE is that there is no range in RMSE. RMSE can be -5,000 also, it can be +5,000 also, it can be -30,000 also, it can be +30,000 also. All right. So which one is correct? Like I don't know, like how much is fine? Is whether this 3,300 or 5,500 or 4,400 that we see, whether it is low error or high error, that we don't know. Okay, so we need something which can tell me whether I have performed good or not in case of regression. And that's where comes the concept of R square value. Okay, let's try to understand what R square is. Everyone got what the issue is with with the regression model?
Yes, one question. So, RMSE here is 3, right?
Yes.
So we are saying the result is, pass if the predicted value is falling between the range, ±3 of RMSE, like 160.
Right. Yes.
Right?
Only. Right. You're right.
No. Okay.
Okay. We are saying that we are on an average off by 3. Right. So it means that yes, I can be like 3 plus as well, 3 negative as well. Like, but on an average, I'm off by 3.
Okay. Yeah, got it.
This RMSE and R square is similar to this covariance and correlation, right? Like you're standardizing the range.
Yes, very nice. Yes, you're right. We are standardizing, that part is correct. but we are not going to standardize RMSC. Okay. Concept wise, you are right that there is a problem with the covariance, that it was not standardized. Correlation was something which has a fixed range, 0, -1 to 1, right?
Yeah.
But correlation was directly derived from covariance.
Yeah.
But R square will not be directly derived from RMSC. Okay. The problem is same, right? But the solution is a little different.
Okay.
Okay, let's start. So let's say um, this is the height of someone. Okay. Let's say Rahul. This is hmm, this is height of Rahul. This is the actual height. This is the actual height that I'm trying to predict. Okay. If I only know the gender of the person, okay. Hypothetically, if the question that we have is, you need to predict the height. Let's say we need to predict the height of this person and we don't know anything about that person. Let's start with that. I don't know anything about this person.
And I mean,
Okay. What we will do in this case? If we don't know anything about that person,
We just see the x value, then the constant if it's given, and the coefficient of the height, then we will like calculate the y value, then we will get the height.
right? No. So if nothing is given, then our best prediction is the average. Okay. If nothing is given about a person, then our best prediction is going to be the average. So let's say this is the actual height, right? What I will do is my prediction is going to be, this is the actual height. And if nothing is given to me about that person, maybe what I will do is I will predict average height as a height of that person, right? So the person's height was this much, but my prediction was this much, right? This is my predicted value. This is my predicted value. Okay, so this much will be what? From here to here. What will be this?
Error.
Error.
Error. Right? Now, the same thing I'm going to do is just that now one additional information is given to you. Okay. Earlier, nothing was given. Now it is being told to you that this A person that we have is a male. So I will say that, okay, whatever the prediction that I had made last time, I'm going to add a little bit more on top of it because you have given me that it's a male. Okay, so the average height will be a little bit more as compared to what it was, that what I predicted last time. Okay, so now what is going to happen? My error will become this much. This is my now final height is, right? This is the final prediction is.
As we have like more meaningful features, error will decrease.
Right. More variables we will add, more accurate it will become. Right. So now earlier the error was this much. Now the error is this much. Right. When you have told me that there is that person is male, my error has reduced. Okay, but still there is some error which is pending. That's correct, right? So this was the average. This was the I added this much additional. Why? Because you told me that that person is male. So this became my final height. Okay. So let me write it down here. Right. This is my total predicted height. This is my total predicted height. Okay. This is what my actual height was. Okay. And this is how much my error will be. Something like this. Here I will get the error. If you will add more variable, it might improve. If you will, if you will not add this variable, then maybe this is going to be my final prediction. Right now, if I'll combine these things together, this much will become my actual. Right? C is my error. So let me write this down. A is what? A is the average height. What is B? B is the incremental height that we have predicted based on our variables. Incremental model improvement, I will just call it. Based on input variables. Right? I was able to predict B, right? I said that, okay, no, it's not going to be A. It is going to be A plus B because the variables that I added was relevant variables, right? Gender is a relevant variable. Whatever is remaining, but still there will be some part that I will not be able to predict. Why there is some part that I'm not being able to predict? Why I'm not being able to predict the exact height of someone? What could be the possible reason?
Because we don't have
Accuracy.
like all the information.
Right. Because we don't have all the information. Right? They like all male are not of the same height. Right? All female are not of the same height because there are many variables which decide the height of someone. Diet, parents' height, your ethnicity, right? Uh, and all of that decides whether what is going to be the height of someone. And many more variables. Obviously, if it was just the gender, just the ethnicity, just the parents' height, then everyone with the same ethnicity, same parents' height, same gender, would have had exactly the same height, right? But that does not happen because there are many other variables that maybe we are not aware of, but are still, or maybe we are aware of, but it's very difficult to capture, are still influencing our height. Okay. So A is what? A is the prediction which is in the absence of any variable. B is the incremental prediction or improvement that we are being able to make based on the input variable. And C is still the error that we have, something that we are not being able to, predict even after, like we need additional variables to capture this information. Okay. Now, when it comes to linear regression, what we say is this B plus C that we have, okay, B plus C, this B, okay, this B plus C that we have is the total variation from the mean. Is that correct?
Yes.
Right? How much the height is varying from the mean, and there can be many reasons because of which it might be varying, right? A lot of different things are there which influences someone's height. So someone's height can be more than the mean as well, someone's height can be less than the mean as well, right? But this is my total variation from the mean, B plus C. B is out of this total variation, how much variation is explained by my model. Variation explained by the model. Right? Ideally, I wanted my model to explain all the variation, right? If let's say I'm 5 feet tall, I want my model to explain that why this person's height is 5 feet tall, right? Why it is not 5.2, why it is not 4.8. I want my model to explain that part, but obviously my model will not be able to explain the 100% the variation. Some variation it might be able to explain that, okay, this person is a little taller, maybe because of his gender. Okay, so the remaining part, we call it, whatever you are not being able to explain, we call it unexplained variation. And unexplained variation can be because of many different things. It can be because of the variables that I am not aware of. It can be because of the variables that I'm aware of, but I'm not being able to capture. Okay, for example, diet. I know that diet is going to have an influence on the height of someone, but I don't know how to define diet. Right? How would I say that this diet is better than the other diet? And if this diet is better than the other diet, by how much it is better? Right? So I know that the diet is going to have an influence on the height, but I'm not being able to capture it as a variable. Okay. Now, this B plus C that we have over here, that is the total variation from the mean. Right? Is also called as SST. SST is nothing but sum of square total. B is called SSE. My bad, not SSC. B is also called SSR, sum of square regression. And C is also called SSE, sum of square error. Okay, I'll write it down. SST is also called sum of square total. That is our total variation from mean. Sum of square regression, that is nothing but how much your model is being able to explain, and SSE, that is sum of square error. How much my model is not being able to explain. Okay, the best case scenario would have been when my model will be able to predict exactly the same height. Okay, so what is R square now? Hey, this is the important part. We are doing all of this because we wanted to calculate R square. R square is nothing but SSR divided by SST. The total variation which was there in the data set, out of that, the total variation was how much? This was the total variation in the data set.
B plus.
B plus.
Right. And how much I'm being able to explain out of it?
B.
B.
Okay. So R square is nothing but the total variation that your model is being able to explain divided by the total variation that exists in the data. Okay. Now, what can be the range of R square?
0 to 1. 0 to 1.
0 to 1. Okay. R square is going to be between 0 to 1. The minimum value can be 0. The maximum value can be 1. If R square is 0, what is the meaning of that?
That the model is accurate, 100% accurate.
No,
If the model is no.
not accurate. 0 means
It is 0.
bad.
Right. So it means that the B part is 0. What is B? B is the explained variation by the model of the total variation that existed in the data. B is the variation that was explained by the model. So if R square is 0, that means B is 0. It means that the model is not explaining any variation in my data. Okay. What is the meaning of that?
We don't have enough information.
The height is not, I mean, we're not getting the height correct value regarding the.
Right. Nice. Right. Exactly. My model is not being. Now, one more thing that I want to kind of cover over here is just 1 minute. I will explain. The predictive. Let me delete the unnecessary slides. Yes. Okay. Now,
Puneet, I
whenever
have
it
a
is.
question.
Uh-huh.
Yeah, in real time scenario, where does B come? Actually, we give the entire data, right? We don't give the data in parts. So
Yeah.
when does B come in real time scenario?
So you have given the entire data set. My model is going to get trained, and my model is going to predict the value. What my model is going to predict? My model is going to predict this much, A and B, right? Is that correct? Once my model has made the prediction, can I calculate what is B? Let's say my model has given me A and B together. A plus B is a prediction, right?
No, actually, this B is the thing which will be added when there are some additional information given to the model, right?
Additional
I'm asking.
information on top of what? Nothing. Okay. Additional information on top of nothing. If nothing was given, then this B is on top of that.
Okay.
It's not like that you already had 5 variables and I added the 6th one. No. You had 0 variable and I added 5. That is what B is.
Yes.
Okay. So once you will make the model, you will get the final prediction. Once that prediction is made, you can calculate B by subtracting the average value. Okay, that will be your incremental. Okay. Let me explain the next part. Maybe it will become a little bit easy. So I was saying in classification, okay, when you are trying to predict, let's say yes and no, just male and female, right? When you have a classification model, the answer will either be right or it will be wrong. Okay, but what is, do you think is the minimum accuracy which is there in a classification model? Can anyone tell me, like, what is your guess? What is the minimum accuracy that can be there? And I'll tell you, the answer is not 0.
0.5
50%.
middle.
The answer is not 50%. It will depend upon something. It's a variation. Okay, let me tell you, it will not be like it is 0.2. It is 20%. It is not 30%, not 50%. It will depend upon which data I'm using. But based on that data, I can tell you that this is the minimum accuracy that you will get. Now you tell me how you will calculate the minimum accuracy for any data set. It's a common sense question, to be very frank. It's not
Like
related to machine learning.
difference between the predicted and the actual one. And we can just find
No,
the
no.
accuracy.
I'm just saying, if I will give you just a data set, just your target variable, you can tell me that this is going to be the minimum accuracy of this data set. How will you tell me that? Without even any input variable, just the target variable if I will give you.
At least one is true.
At least one. Its maximum is 1, right?
I mean, if there are 6 columns, at least one prediction is true, then that's the minimum, right? If there are 6,
No. So you are telling me once you will make the model, then you will tell me what is the minimum accuracy, right?
Yeah.
I am asking, without even creating a model, if I want to create a baseline, right? That your model, if it is less than this much, then your model is totally useless.
0.001. Maybe we'll take very less only. Then according to it, we can just update it.
No. Think, there is very logical answer to this. In some cases,
80%.
no. Let's say if 80% is actually considered a very good accuracy, not minimum. And why 80%? I'm saying that from data set to data set, it will vary. But 80% is the one constant answer you are giving me, right? Okay. Think how can I calculate the minimum accuracy that I can have for a model, for a classification model? And I'm telling you, it will vary from a data set to data set. It will not be a fixed value.
Like,
if we calculate the RMSE of the data set and we then calculate how it is differing from the average of the dependent variable. So by that we can calculate how the model is gonna be like, so the variations on.
But for RMSE, you need to have a model first, right?
Okay.
I'm just saying that you have not even created a model. Give me a target variable, and I will tell you what is the minimum accuracy without even, like, I don't even know how many input variables that you have.
like it depends on the number of classification values. Like if we have true, false, or anything else, then the minimum accuracy would be like 1 by the number of variables or number of classification values, 1 by.
Right. Very nice. Okay. So actually, what happens is that, let's say in any data set, let's say if I have some data set, let's call it data set 1. Okay. There are in classification, let's say there will be 2 classes, 0 and 1. Now this 0 and 1 can be pass and fail. It can be male or female. It can be, the loan should be given, loan should not be given, or it will be churn, it will not be churn, right? So 2 classes are there, 0 and 1. If my 0 is 90% in the data set and 1 is 10%, then my minimum accuracy of this particular model should be at least 90%. Why? Because even if I will classify everything as 0, if I will create a model which is just classifying everything as 0, what is going to be the accuracy of that model?
It's minimum 10%.
No, it will be 90%. If I will classify everything as 0, so for what percentage of data set you will be correct?
Okay, 90%. Yeah.
90%, right? So even if I'm creating a very basic model, which is without any variable, the minimum accuracy that I will get is 90%, right? Similarly, if I have some other data set, let's say data set 2, where this is, let's say 45%, this is 55%. What will be the minimum accuracy of this data set?
55%.
55%, right? Because if I will classify everything as 1, the accuracy that I will get is 55%. Is that clear to everyone?
No, I didn't get what is 0 and 1 here.
0 and 1 is 2 different classes, right? You can, let's call it, churn versus not churn. Or let's say I'm trying to predict whether someone will have cancer or they will not have cancer, right? Whether someone will have diabetes or they will not have diabetes. Is that clear now, Nikita?
Yeah. Like we are predicting it is 90% the person will have cancer and 10% not.
Correct. In your data set, 90% of the people have cancer, 10% does not have cancer in the data set itself. It's not prediction. Okay. In some other data set, 45% have cancer, 55% does not have cancer. Right. So I'm saying that depending upon this ratio, I can get what is the minimum accuracy of a data set. Let's say if I have in some other data set, this is 30%, this is 70%, then what is going to be the minimum accuracy of this data set?
70%.
So this
70%.
cancer and not cancer is the Y variable you're talking about, right? Output variable.
Right. Yes, yes.
Sir, don't we take the minimum of both the values? Like
No,
when you're
let's say-
saying 70%, it's
Uh-huh.
we are taking the max of two values.
Right. Yes.
And to determine minimum accuracy, we should be
Uh-huh.
taking the minimum of those values, right? Not the max.
So let's say if nothing is given to me, let's say in data set 3, if nothing is given to you, right, and you need to make 100 predictions, nothing is given to you, right?
Okay.
For every right prediction, I will give you, let's say, 100 rupees. What will be your prediction for each value? Not cancer or cancer?
Okay. Understood. Yeah.
Right.
So I'll try to find out the best possible answer on
Exactly.
those values. Okay.
Right. You will, like, if I'm giving you 100 rupees for each correct prediction, you will say for every prediction, not cancer, not cancer, not cancer, not cancer. Why? Because you will be 70% accurate. But if you will say cancer, cancer, and cancer, then it will be only 30% accurate. Okay.
But again, it depends. Like, what are we trying to find out? Like, what is it, cancer or not cancer?
No. First of all, between cancer and not cancer, I cannot choose. Right?
Okay.
It is just the two sides of the same coin.
Okay.
Right? Whether I will be giving loan to someone or not giving loan to the someone, whether you will try to predict, okay, yes, I should give this person the loan, or you try to predict that I should not give this person the loan, it's one and the same thing.
Okay.
Right?
But when we are calculating the value for not giving loan, so the values will differ, right? Like it will not stay 70% or 30%.
Why?
I mean, if we are for the data set values that you have written currently on the screen, so I'm trying to find out the not cancer probability or the not cancer. Then
Okay, not cancer probability will be same as 1 minus cancer probability.
Okay.
Right? It will just be a flip.
Okay, got it. Yeah.
So, Puneet, for
But
your second data set, 45 and 55, and suppose it's divided test data and trained data are 80 and 20.
Right.
So there might be chances that 80%, probably 75% is non-cancer data
Right.
is picked and only 5% got my question, right?
Right. I
20
got it.
ratio, it gave inclination to 55%.
Right. Yes,
So the
it can
predictions
happen.
will differ, right?
Right. It can happen by chance, but in general, if you look at it, we are doing a random sampling. We are doing a random split. So in general, when you have a big data set and you do a random split, and if this is what your original data set was, right? Believe me, when you will do a test and split, it can happen that in training, maybe the first one is, let's say, 43%, and the next one is, let's say, maybe 57%. In test, it might become, let's say, 46%. Another one is, let's say, 55%. This much variation can be there. Okay. But it will not be that in training, I have, let's say, 43, 57, and in test, it will become 30, 70. Okay. Small
Yeah.
variations can be there because it is a random split that we are doing, but huge variations cannot be there.
So is there a way like tuning things because we are splitting 80-20? So like one prediction may be differed from one data set prediction can differ with the other data set prediction, right? So
Right.
is there any performance tuning methods to get
Actually,
better
you should
accuracy?
not tune it on train and test at all, right? The idea
Okay.
is that, like, the whole idea behind test and train is that I don't want to interfere. Okay.
Okay.
I just want to randomly split between 80% and 20%. 80% I will be training, and the remaining 20%, whatever is there, right? I will try to predict how much accurately I can predict on that data set, because you don't know whether, let's say, even in the future, when the new data set will be coming, will it exactly be the same as what the data set that you have trained on? No,
No.
right?
Yeah.
Even the future data set can have a few variations, right? So the best thing that you can do with the train and test split is not to tune it.
Okay.
Keep it random. Let it
Okay.
be have some variation.
Okay. But the
Okay.
variation will always be less.
Yeah,
That's
yeah,
what.
exactly.
Yeah.
Because see, even in the future, if today, let's say think it from a bank perspective, today, certain percentage of loans they are rejecting because maybe they feel that those are fraudsters, or these are the people who have very bad credit score and all, right? So maybe they are rejecting 10% people today and approving 90%. Even in
Okay.
the next 1 year or 2 years, this split will not change drastically. It might
Yeah.
happen that from 10%, the applications of fraudsters might increase to 12%, 15%, right? But let's say
Yes.
if in future it splits to 50-50, that because of some reason now 50% of the application that SBI is getting is from the fraudsters who are trying to trick the system. In that case, the old model will not hold true. We would have
Yeah.
to retrain the model.
Yeah. Got
Okay,
it.
so we always assume that the future data will have some variation, but obviously the variation will not be huge. If that happens, then today's model will not hold true.
Okay. Thank you.
Yeah, sure. Okay,
So this
so
is like we are gathering initial information like how biased the data is and how we can split it into like zero on the other side and one on the other side. Like perfectly. Isn't it the the base idea of decision tree also? This is also what we do in decision tree in the starting step. We just split it between zeros and one, then further we go down the tree. So like so it's like kind of classification we use this in like
right. Yes,
decision
yes.
tree also.
Right. You're right. And similarly, if I'll talk about the regression part, okay, if I'll talk about regression, uh, similarly, if I'll talk about regression, now tell me what is going to be the minimum error in this case. No, sorry, what is going to be the maximum error? From accuracy perspective, I talk about minimum accuracy. If I in regression in general, we don't talk in terms of accuracy. We talk in terms of error in general. Okay. What is the maximum error that I can get in case of regression? Right? Let's say if I'm trying to predict the price of a car, okay, I'm trying to predict the price of the car, and let's say the range of the price of the car is between 10 lakh to 20 lakh. Right? And then if I give this kind of a data set to someone and if I ask them, right, what do you think can be the minimum or max, what do you think is going to be the minimum and the maximum error? Minimum error, everyone knows the answer. What can be the minimum error on a data set?
0.
0, right? That I'm being able to exactly predict the price of the car. And when I say what is going to be the maximum error for this, the people say that, okay, it can be anything. It can be, let's say, 30 lakh also. Who knows? Error can be 1 crore also. There is no limit to it, theoretically, right? But actually, there is a limit. How can I calculate what is going to be the maximum error in this data set? We calculate the maximum error
Mean
in
square.
the data set by benchmarking it with the average model. Okay. The most basic model which can be created for a regression is average model. Okay. That is, if I will predict the price of the car as the average car price. If you will predict the price of the car as the average car price, you will get some accuracy. Is that correct? If for each car, if I will predict the price as the average price, you will get some error there, right? That is the maximum error that I am expecting. If your model performs poorer than the average model, that model I will not be using at all. Because we assume that the worst kind of prediction that you can do is the average. You got my point? Let's say if I have hypothetically, I have a lot of people and this is their height and this is what the people are, customer 1, customer 2, customer 3. Let's say this is height of one person. This is height of another person. This is height of one person. This is height of another person. This is another person's height. Let's say I'm just plotting the height of each individual. Okay. What is the best accuracy that, the best thing I can predict for each individual? The best I can predict is that whatever their height was, I was able to predict exactly the same. This is the best which can happen. For each individual, I'm being able to predict the height as it is, right? See, this is customer 1, customer 2, of whom I'm trying to predict the height. This is the best which can happen. Whatever the height was, I was able to exactly predict that. And when I ask people that, okay, what is the worst which can happen? The people say that the worst which can happen is I will predict everyone's height as 0. Right? This is the worst which can happen. But the answer is no. That is not the worst which can happen. The worst which can happen is, what will be the worst?
Average.
Average, right? This is the worst which can happen. Worst model. Okay. So when you will be measuring the performance of your model, when you are measuring the performance of your model, you will not be measuring it from 0. You will not say that, okay, if this model was not there, I would have predicted everyone's height as 0. Right? No. If this model was not there, I would have predicted everyone's height as average. So how much your model is contributing, that will be calculated on top of average. Is this point clear?
Yeah.
Right? Because R square exactly does that. When R square is 0, that does not mean, right, that I am predicting 0 for everyone. No. When R square is 0, it means that your model is same as average model, because that's the worst which can happen. Okay. R square equal to 0 means the meaning of R square equal to 0 is not that you are predicting, like, let's say if the price of the car was 10 lakh, I have predicted it as 20 crores. No. R square 0 means that if your model, right, R square 0 means that model is same as average model. Average because this is the worst which can happen. Okay, that's why if you look at it, R square is what? If you remember, it was B plus C out of B plus C. What was B plus C? The B plus C was the variation from the mean. That whatever is the variation from the mean, out of that, how much I'm being able to explain. Because why I am considering that this much is the only variation that I have. Why I am not considering that this is the variation? Because we assume that the variation can only happen on top of average, not from 0. Because I should not measure how my model is performing on top of 0. No, I will be measuring how my model is performing on top of average model. Because that will give me the true picture, right? That if my these variables were not there, I will not predict the height as 0. I will predict the height as average. So how much you are improving the model on top of average is something that I'm interested in. Okay, now if you go back here, the R square is 66%. What is the meaning of this? It means that of all the variation that existed on top of average, all the variation that existed on top of average, I am being able to explain 66% of it, right? So it means that hypothetically, if let's say if this was this much was 6,000, I am being able to predict 66% of this 6,000. Okay, I am being able to predict 66% of this 6,000. Okay, that is what my R square is. So R square tells me that, okay, I could have improved my model further by 40% more, or let's say 34% more. Is it clear to everyone? Right? In general, R square value more than 70% is considered actually good. Right? That you are being able to predict 70% of the variation. No one can, like, at least for any decent data set, no one can predict with 100% accuracy. Okay.
Can you explain the example now? It was 6,000.
Yeah. So I was saying that, let's say if this much is 6,000, hypothetically, if this much was 6,000, my R square value of 66 means that on an average, like this is again, this 6,000 I'm assuming is on an average is the distance between the average value and the actual value. Okay. And my 66 R square equal to 66 is telling me that on an average, I am being able to predict this much on top of average. Okay. Which will be how much? Around 3,900. Right. So my B is going to be 3,900 approximately. You got my point?
No, sir. Please explain that once again.
Right.
No,
Let's assume this difference that we have between the average and the actual value on an average is 6,000. Okay. My R square value of 66% means what? 66 R square value is what? B divided by B plus C. This is coming out to be 0.66. If B plus C is 6,000, how much B is gonna be? Approximately 3,900.
Okay. Okay. Yeah. Yeah. Got it.
Okay. So it means that over whatever the variation which was there, I'm being able to explain 66% of it. Whatever it was, I assume it to be 66,000. It need not to be 6,000. But whatever it was, I'm being able to predict 66% of it. Clear? Okay, guys, we will take a 10 minutes break. We'll see you after the break. Hello. Let's start. Right, so we were discussing R square. R square tells us that of all the variation which exist in the data set, what percentage of that variation we are being able to explain. Okay. Now, one of the formula that like we can use is this. Okay, I'm just making one line. This is your predicted line. Okay, this is what your predicted line is. Let me think. I was thinking of something. 1 minute. One minute. I think I should draw it a little lower. Maybe let's say here. Okay. Now this is what our predicted line is. Okay. The equation will be like always y is equal to beta naught plus beta 1x. Okay. Now let me draw average line. Okay. Now, if this is my average line, let's call it y mean. Okay, this is what the actual value is. Let's call it yi. Okay, where will be my predicted value? My predicted value will be this. Just below this, here. This is what my predicted value is. For this given xi, for a given xi, this is what my predicted value is. Now, if I would have to make, dot B, C, and A, right? Let's go back to this chart. What was A? A was from 0 to average. So if I would have to draw A over here, A will be this much. Right? This is your A is. Similarly, what is now B? B is from average till predicted value. So from average till predicted value, this much is your B. Right? And this is my error. From here till here, this is the average that we error that we have. That is C. So I have A, B, and C. C being error, B is the variation explained, and A is, let's say, your distance from 0. Okay. What was B? B is the variation explained, right? B is the variation explained. B plus C was total variation. And C was the error. Right? There is one more terminology for this, which is B is called R. This is called SST. And this is called SSE. There is a relationship between these as well. Again, not important, but good to know stuff. SST, sum of square total, is going to be equal to sum of square regression plus sum of square error, which makes sense as well, I believe. Right? The total variation is nothing but the variation that was explained by my model versus the explanation, the variation that was not explained by my model will be equal to total variation. Okay. Yeah, this much on this. Then I think the last topic for today will be VIF. Let's see what VIF is. But before we go towards VIF, okay, before we discuss VIF, which is nothing but variance inflation factor.
Can you please go back to previous screen once?
Sure.
Yeah, thank you.
Yeah. Okay, variance inflation factor. But before I go over there, right, let me ask you a question. If price of the car is given by approximately 159 times horsepower minus that 32 something, right? What was it? 3283, right? So price of the car is this much. Okay. My question to you is, what, and it has some accuracy, let's say accuracy or RMSC. Let's say the RMSC associated with this is 5500. Now, I did one more thing. What I did was I added one more variable, which is horsepower. Again, exactly the same variable I have added. Okay, I have added one more variable, which is exactly same as horsepower. So my price of car will become something, obviously, multiplied by horsepower plus something multiplied by horsepower 2. A duplicate variable is there. Okay. Minus 3283. Now I have a few questions for you. Like first thing, what is given to you? Horsepower is exactly same as horsepower 2. These are the two same variable which is there. Or let's say this is, let's call it RMSC, maybe A. Okay, I am calculating another RMSC for this model.
RMS is error, right, from actual value?
RMSC is the error value, yes. Root means square error. Okay, in case B also you will get some error. I don't know what it is, right? But I want you to tell me whether between RMSC A, that is the error for first model, and the error for second model, which error will be more? Will it A be more than B,
RMSE
or B more than A, or both being equal?
RMSCA should be greater than RMSCB.
Okay, so you are saying
B
that
is
this
going to
second
be
model will be
equal.
more accurate than the first model.
Yeah.
Right?
Well,
But it's the other way around, right? Like we are introducing one more variable, so error will increase.
Why? Introducing more variables should improve our model, right? If you will,
It will improve the model, but it will reduce the accuracy, right? I mean, a bit.
why? Like how can you improve a model and reduce the accuracy? Right? Improving the model means that your accuracy is increasing. That's what we mean by improving the model.
Yeah, yeah. What I meant is like it will increase the error by bit, right?
I think he's trying to say if we are introducing a new variable that would uh, uh, give more room for error while introducing a new variable.
Nee, okay, but let's
No,
say we're trying to predict
if
height
we
of
like
something.
introduce new features, the error get decreases. No, if we include new
Right.
features,
Now, let's say,
the
for
error
example,
decreases.
if you are, I am asking you someone's height, you said that it is average, right? I told you that, okay, he's a male. So your model will improve or the accuracy will go down if I'll tell you the gender of the person.
No,
Model will
accuracy will
improve.
increase here, but that error, what I'm trying to understand, it will increase, right?
How both the things can happen, Sumit? Like, how can accuracy increase at the same time error can also increase? Both are complement of each other, right?
Okay.
You got my point?
Okay.
Error is nothing but 1 minus accuracy in general,
Okay.
right? Introducing more variables in general increases the accuracy, which reduces the error. Is that correct? Like, is everyone on board on that?
Yes.
Right? But if I will tell you that, okay, this is not correct, what you have told me, then can you tell me what will be the right relationship between the two? Okay, let me ask you this. I first asked you to predict the height of someone and you had no information about that person. So you predicted the average height, maybe let's say 165. Then I told you, no, that person is a male. So you said, okay, for male, my prediction is going to be, let's say 170. Now I again told you, no, it is male. Will you change your prediction?
No.
No.
Right? Will you increase it, decrease it? Nothing, right? So if I'm providing you the exact same information again, right, your error will neither increase nor it will go down, it will remain the same. You will not change your prediction just because I repeated something twice.
Oh, they were equal.
Yeah, it will be
Yes,
equal,
you do.
right? The model will not improve, the model will not become worse. It will exactly, like, it's like, just imagine, hypothetically, if it was improving. Hypothetically, it was improving, let's say. So why to add just one more time? Why not to add 3 more times? The model will improve even further. Why not to add the same variable 10 times? The model will improve even further. Let's add the same variable 100 times. The model might become 100% accurate. You got my point? If my model accuracy will improve by adding the same variable again, why to stop at once? Why not to do it twice, thrice, 5 times, 6 times, 100 times? Right? So always remember this example. By telling you the same thing again, you are not going to change your prediction. If earlier I said 170, even if you will say that, okay, no, he is male, I say 170 only. No, he is male. Okay, yeah, 170. Right? Until unless I give you a different information. If I will say that, no, he is, let's say, 25 years old. Now, this is a new information. At the same time, it is a relevant information. If it is a new information and it's a relevant information, then your accuracy will improve, and that's when your error will go down. Okay? Otherwise, the error will not change. Is it clear? Like, make sense to everyone?
Yeah, if we take the same variables, there is no change in the error.
Right. Okay. If it is the same variable, nothing will change. Okay. What about now? Let's say here, this is B1 and let's say B2. Can you make any prediction about B1 and B2? Okay, let me tell you one thing. According to the model, right, does the model have any preference in terms of whether it is horsepower 1 or horsepower 2? Can it differentiate between the two?
No.
Yes.
No,
If they are
that's
equal, no. If they are
if they are equal, then the model cannot differentiate. The model cannot say that, okay, this is the same horsepower that you used in the first iteration. No, then when you are providing these two inputs, these two have the same importance for the model. The model cannot say that this variable is more important than the other. Okay, and the both are gonna have the same impact on the price of the car. Okay, or let's think it from this perspective. Okay, can I say that if this was horsepower 1, can I write this equation like this? B1 horsepower 1 plus B2 horsepower 1 minus 3283. Are these two equations same?
yes.
Yes, right?
Yeah.
Because horsepower 1 and horsepower 2 are exactly the same. Then can I say that B1 plus B2 is this is also correct?
B1 plus P2 equals to 159. You also say that.
Very nice, right? So B1 plus B2, that means is equal to 159. Okay, so I'm gonna say is equal to 159. Now tell me, because the model is not having any preference towards either horsepower 1 or horsepower 2, don't you think that most probably this will happen, that B1 will be same as B2? Right? Because I have no preference.
Yeah.
I cannot say that horsepower 1 is more important than horsepower 2 or horsepower 2 is more important than horsepower 1. So what I will do is I will equally split it. If this is correct, can't I say here 2 beta 1 is equal to 159?
Yes.
Which also means that beta 1 equal to beta 2 will be equal to 79.5. Yeah, I'm doing it right? It's 160, then 80, yeah. Okay. So it means that if I will, the important points from here is, right? First of all, this will remain the same. The error will not increase, the error will not decrease. The second thing is, you will see that the coefficients will change. Okay, hold on to these 2 points and we will run the code and we will get back to these 2 points. These two are very important points.
How this beta 1 equal to beta 2?
Because I'm saying that my model cannot make any preference between horsepower 1 and horsepower 2. For my model, both are exactly the same. Right? So on what logic I will make B1 greater than B2 or B2 greater than B1? Right? If my model is gonna say, hypothetically, if my model is gonna say that this is going to be 100 and this is going to be, let's say, 59. My bad, not here, but here. If my model will say that this is 100, this is 59, right? My question to my model will be, on what basis you have decided that beta 1 is going to be 100 and beta 2 is going to be 59? Why you are saying that this column is going to have more impact as compared to this model, this column? You got my point? My model cannot explain that part.
Yeah.
That why one coefficient is bigger than the other. So because my model is very intelligent, my model is going to say that, okay, if you have given me two exactly same variables, what I will do is I will give them half of the coefficient each.
Oh, if HP1 won't be equal to HP2, then it would be different.
It will be different. Yes. Then it is two different variables, right? Then it will be different. Any question on this slide?
So instead of we are splitting the horsepower into two different variables. I assume that HP2 is a different variable which is unrelated to the horsepower. That's why I said error A is greater than error B. So would
No.
it be that?
Actually, I had mentioned this part that that horsepower 1 is same as horsepower 2.
Yeah, that I didn't take into the consideration.
No worries.
Yeah, understood.
Now is it clear, right?
Yeah.
Good. Now let's try to do the same thing here also, like in our Python notebook. Right. What I'm doing is I'm gonna add a duplicate variable. Nothing. Let's say last time I forgot the name of that person. He asked me that can I just simply do this instead of using that function constant? Can I simply do like this? He asked me, can we do this? I don't know who it was. Const equal to 1. Can we do this or not? Right? Yes, we can do that. Because same thing I'm doing here. I'm just saying that the horsepower column, horsepower underscore 2 column is same as horsepower column. So I have created a new column which is same as horsepower. Now, what I will do is when I am creating the model, before creating the model, we always separate the independent variable and dependent variable. So these are all my independent variable. This is what my dependent variable is. So I will run this. Okay. Then after this, exactly same code I'm following. I'm adding one constant. Then I'm splitting the data into test and train. And then I'm fitting the model. Right. Now, if I look at the summary of the, summary of my model, you will see that it is exactly same as what we got last time. Okay. R square is 66%. Your constant is -3283, which was this. And my beta 1 and beta 2 is nothing but half of what it was earlier. Right? Last time it was 158 point something, right? Like, let's look at what was the exact value. 158.78. Right? It is exactly half of that, if you'll check. 79.39. Okay. The p-values are also less than 5%. So it means that it is saying both the variables are important. Right? Now, this was an example just to show you that, okay, what happens when we add a duplicate variable in the data set, right? Obviously, I will never do that. Intentionally, I will never do that. Okay, but it can happen by mistake. You guys agree? Let's say if I have 5,000 different variables, right? And there is two variables in this, right? I have 5,000 different variables and there are two variables in this. One is HP power, other one is horse underscore 2. How would I know that these two variables are exactly the same? Right? If I have 5,000 variables, there is no way. Now, when I will be running the model, keeping these two variables, one variable being, let's say, h power, another variable being horse underscore 2, right? I will be I will be putting both the variables in my machine learning model, and both the variables will come out important. Okay, what is the problem with that? Is there any problem with that if that happens? Let's say if I have 5,000 variables, out of which two variables are exactly the same. It's just that I never realized it because there are so many variables. So I put all the variables in my data set. On both of these variables came out to be important. My question is now, do I have a problem with this? Will this have any impact on my accuracy? If this happens?
Will it not create bias because like for each singular value there is another same?
Mm-hmm. No, but will there be any impact on the accuracy if that happens?
If we like calculate the accuracy for h power, it will be equal for uh like those two, and if we combine them, it will be then also will be equal.
No. So let's go back to the previous example. If there is a duplicate column in our data set, will it has any impact on the accuracy or not?
No.
Oh,
No, right? My error is same. So it will not have any. So impact on accuracy? Answer is no impact. The accuracy will not change. Impact on coefficients?
Will change.
Yes.
The answer is yes. What happens is coefficients become unreliable. I will explain what it means.
Generally, how we define the coefficients? Just
Coefficient
like,
is nothing but this: beta 1, beta 2, beta 3, beta 4, beta naught.
yeah, but I'm asking meaning.
Meaning is that 1 unit increase in, let's say, for example, if I will say price of the car is nothing but 159 into horsepower minus 3283. What is the meaning of this 159? The meaning of this 159 is that if I will increase my horsepower by 1 unit, okay, my price will increase by $159. If I will create a new engine which is let's say 10 horsepower more than the previous engine, then my price of the car will increase by around $1,600, 1590. Okay, so 1 unit change in horsepower will result in $159 change in price. That's what coefficients mean. Okay, now the problem is that if there was a duplicate variable and I was not aware of it, this will become 79.5 horsepower 1 plus something, 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 something. Right? Now what I'm saying, 1 unit change in horsepower 1 column, that is horsepower, will result in $79 change in price of the car. Which one is more accurate? The first one or second one? Which one is correct?
Both
This one?
are accurate, equally accurate, but it is more favorable to use the first one.
Right. So, but my question is that if I will increase the horsepower by 1 unit, in reality, how much the change will happen? $159 or $79?
159.
159.
159 will happen, right?
Yeah.
So it means that if I'm accidentally using a duplicate variable, then my coefficients become kind of useless.
Yeah.
Right? Because I will be expecting that if I will increase the horsepower by 1 unit, my price will change by $79. But it will actually change by $159. So my prediction will be wrong in terms of horsepower. But overall prediction obviously will be correct. But if I will try to measure the impact of one particular variable, that will be incorrect. Okay, so if your only goal is to measure the accuracy, all you want to do is at the end of the day, you want to predict the price of the car. You don't care how horsepower is related to price, how weight is related to price, how height is related to price. I don't care. I just want final prediction. I don't want to know how individual variable is related to the price, right? Then I'm not worried about having duplicate or related variables. But if I'm I'm interested in understanding what is the relationship between variable and the target variable, the input variable and the target variable, then I need to make sure that related variables should not go into the data, right? But if I look at this summary, to be very frank, using p-value, I cannot exclude any of these variables. Both the variables are coming out as important. So it means that I need to have something else. That something else is VIF. Okay, that something else is, if you look at the accuracy also, it is, you can check the accuracy. It is same as what we had last time. 4400 for training and 5500 for test. Exactly same. 4469. See? 4469. 5516. 5516. So by adding a duplicate variable, my error is not changing. Okay, my R-square value is not changing. But what is changing is coefficient. So this is an extreme example just to make you understand, okay, how a related variable is gonna impact my model. But in general, you having a duplicate variable in the data set, the chances of that happening are extremely low. Okay, but then why we are discussing this? We are discussing this because we have taken extreme example, but all of this theory is also true when horsepower and another correlated variable is there. Okay, let's say for example, your weight of the car will be very much proportional to, right? Let's say length of the car. Is that correct? More is going to be the length of the car, more is going to be the weight of the car. Right? The bigger the car is, more heavier it will be most of the time. So weight and length of the car are correlated variable most probably. Right? So when I will put both weight of the car and length of the car in the data set, right? It can happen that the coefficients become a little unreliable. Okay. So whenever we add related variables in the data from the data set in the model, the coefficients become unreliable, although it is not having much impact on my accuracy. Right? Now to identify such variables which are correlated with other variables, we use something called VIF, variance inflation factor. Okay.
Here,
And this
what is unreliable? I think.
unreliable means that this, like for example, here I would say that this was incorrect, right? This was correct, but my model was giving me 79, which is incorrect. That means it's not reliable to use it because this is giving me the incorrect value. Okay, will I be using this model to understand the relationship between horsepower and price? The answer is no. Why I'm not going to do it? Because coefficient is not correct. Why coefficient is not correct? It is unreliable. This is how we call it. Okay. To identify such variables that we should remove to make sure that the coefficients are more reliable, they are more accurate, we use something called VIF. VIF is gonna identify those variables, okay, which are correlated with each other, and it will tell you that, okay, drop this particular variable, this variable is not needed. So when I'm gonna run this code, okay, it is going to give me like 2.5 is the cutoff. 2.5 is the cutoff. If anything is more than 2.5, then I should drop that particular variable. Now there are two variables which is more than 2.5. So we should drop both of them, right? Right? I will discuss this, but I will discuss it tomorrow. Okay. How we will be using BIF, what we will do next is something that we'll discuss tomorrow. I believe this is all for today. Or tomorrow, actually, next week, then we will be discussing it. Yeah. Okay. So next week we will on linear regression, we are more or less done. We will be the next week we will be discussing multilinear regression. The theory is same, so we will not be spending any time there. What we will be doing is we will be running one more code where we will have multiple variables and we will try to see how the results are changing, whether my model is becoming more accurate, less accurate, and all of that. Okay, we will discuss VIF, and then after that we will move on to logistic regression.
Just a small question.
Mhm.
So the VIF which we are getting, it is 8. So we need to drop both the variables, or we need to merge them.
No, we so whatever so how we do it is whenever your VIF, like let's say you have 100 variables, okay, and you ran the VIF code, and there are out of those 100 variables, 10 variables have value more than 2.5. Okay, you don't drop all the 10 variables at once. You will drop the variable which is having the highest VIF, and then you will rerun the VIF.
Okay, understood. Thank you.
Okay, so we drop the variable one by one. We don't drop the variable at once. Because if you will do that, you will get again incorrect results. Ideally, I should not drop these two variables. I should drop only one. So from here, because both the values are infinity, I can drop any. Okay, so if I will drop that, okay, right. I think I've not calculated it here, but we will calculate it in the next class. So what we will do is we will drop one of the variable and we will see that the for other variable the VIF value will change drastically.
Okay.
Okay, so we will do it one by one, not at once.
Okay. Understood.
Okay, cool. That's all for today. I will upload this file on the Google Drive. Please go through it, whatever we have discussed, so that the next week when we will be running the multilinear regression, at least these concepts are clear to you guys.
So add yesterday's files also.
Yeah, sure. Okay. Thank you. Bye-bye.
Thank you.
Thank you.